But if you have already questions, of course, you can just note them down. So, yes? So what we want to have is that you put the questions after the second week so that Jens can pick up some already, can see already a little bit, and can give maybe some insights. Yeah? And the finally to be graded question and answers we expect at the end of week 4. So you should put something there so that you have something, we can see something, but we will not grade it yet. Yeah? Okay? So there should just be something there, and we can give you some feedback already.
So, so is the format like this? Because you have your question, you have your answer of the question, you have the justification of how you got the question, your reference.
Yeah, perfectly fine.
Like this?
Yeah, perfectly fine.
Okay.
Because I figured when I wrote it, right, I thought you needed to have like the reference from where you would like
No,
get the question
no,
from. Do we need that?
no.
No need, right?
It's you're completely free how to format it
So
at the end. Yeah.
So we can just like, or let's say we just straight away we can just say we justify that we can be able to come up with a question through reference matcha, right?
Can you repeat this?
Okay, so basically, right, since the reference part is negatable, right, but we need to justify that how we derive the question.
Yes.
So
yes.
when we derive the question, right, can we say like, oh, lies, then we take it from online?
That would be good. Yes, something like this.
Okay. But
so
do we
that,
have to
that
specific say which slide number, or we just say the topic number would be fine, right?
it clearly depends.
Depends on. Okay.
Yeah. So it should be specific enough that we can see. Okay, you really thought about this. You have some motivation, and if there's something wrong, we can maybe also pick up. Well, is your source maybe wrong? Huh?
Okay. Okay, I understand. So after that, you just write the review.
Yeah.
Okay.
Good. Okay. So let's start. I was unfortunately in the wrong room first, so that's why I'm a little bit delayed. So maybe quick, because there was the question, so that everybody's on the same page. So the questions, the idea is that you have after the next week, latest, the first 3 questions, after the 3rd week, all 6 questions. Yeah? And you have an initial answer to this. Yeah? Just that you already thought about that, and probably it's already resolved what we had. Then, or this gives us the chance to pick up your questions, to also include this in the exercises, and to see, give a little bit, to see a little bit where the problems are. Yeah? What we will grade at the end is, so you have the option to edit all the stuff until the end of the 4th week. Yeah? And at the end of the 4th week, whatever you have delivered is frozen, and we will grade it. Yeah? So that's the idea behind that. Yeah? And from the formatting, the points which are there on the slides, they should be covered. How you format it, it's completely up to you. Yeah? So ideally in a way that we can read it, so that we see, okay, this is question, this is answer, this is reflection, something like this. But do not spend too much effort in formatting the stuff. Yeah, that's not the main point of this assignment. I've intentionally just gave the option that you can just write free text, because I think that's quicker for you. I mean, you can also put up PDF, but that means that you have to format a PDF, you have to write a PDF, and we have to download the PDF, and we have to read the PDF. Yeah? If it's all in the system, it's quicker for all of us. Yeah? Okay. Then let's do a quick recap of what we did yesterday. We had ended with the SRAM a little bit, and then we had recapped the SRAM. Then we talked about DRAM and ROM. So if we compare DRAM to SRAM, what would you consider benefits of DRAM versus SRAM and vice versa? One rethinking, how many transistors do you need for SRAM? How many for DRAM? Yes? 1 plus a capacitor. Yeah? So DRAM is smaller. So that's a benefit of DRAM. Why don't we use always DRAM? It's a bit slower. What else? we need the refresh cycles, which costs power. So that's in particular if you have something like power islands, if you want to power down a part of your chip, and only keep the memory, then, well, for DRAM you still need the refresh logic to ensure that all the time you refresh your circuit. What else? So we have DRAM usually off chip. Why is this? I think I didn't say it so far, so maybe I have to add this. If you want to implement a capacitor on a device and you want to implement a capacitor in a small way, then you need a specific dielectric. This is hard to integrate with the standard CMOS process. And that is why usually if you have the DRAM, you want not integrate this with a large logic circuit, because it will cost money. So overall, the DRAM is hard to integrate into a complete system. That changes a little bit, or there is a convergence towards having the two chips very close together. Maybe in, don't know, 5 years, 10 years, I cannot longer state this. But at the moment, DRAM is hard to integrate, so it cannot be used for the cache memories and stuff like this. Okay, now if we compare SRAM and DRAM with ROM, no idea why this is not shown at the moment, but well, it's back. If we compare SRAM and DRAM with ROM, what is there the difference? So where would you use ROM versus SRAM? Yeah. So it's read-only, meaning it is either design time programmable. So the version we have looked into a little bit closer, this NAND-based version, this is design time programmable, meaning you as a designer can decide what the program is that should later be run on the chip, boot sequence, something like this, and then it's frozen. You manufacture the chip and it's burned into the chip. There is a second version of classical ROM, which is fuse-based, where you implement this connects that we have looked into yesterday, not by transistors, but you initially have fuses between all these connects, and then when the chip is manufactured, you can burn some of the fuses, and you disconnect here whatever you want to program. As soon as one time's programmed, it's gone. So it's fixed. This is also known as OTP, one-time programmable memory. Okay. There are further variants of read-only memory, of non-volatile memory. We do not talk about, which are up to a certain extent several times programmable. For instance, EEPROM, where you put some charges somewhere in an intermediate gate and so on and so forth. We just skip this. Good. Then we went towards latches and flip-flops. So if we compare directly a flip-flop with some SRAM, when would you use some SRAM? When would you use some flip-flops? Yes, so we put a register bank behind our SRAM, so it's also predictable in timing. You need the sense amp for the SRAM. For the flips you don't need. But where would you use it? So let's think about some roughly how a processor works. Not sure if you heard about that, but what you have is you load from external some data into your core. External, we have DRAM, that we already clarified. We load a lot of data into our core, and then we take from these data instructions that we have loaded from extern, we take command by command into our processor and operate on that. We have this later also a little bit on the slides, but that's roughly the process that happens if you want to run a program on your CPU. Yeah? Now, with that, we load from some DRAM a large amount of data. Where do we load it? In flip-flops or in cache? Or in SRAM? Flip-flops? Well, this is a large amount of data, yeah, several kilobytes. If you put several kilobytes of flip-flops, it will get huge. Yeah? So you put the data from extern first into some SRAM as a buffer. And now, if we want to put this into the processor, then in the processor we have registers that you most likely heard of. The registers are implemented as flip-flops. So, if you want to be small, close to the logic, so small data size, close to the logic, then you use flip-flops. If you have at least several hundred bits, then you would go for SRAM. So, from a logic perspective, you say the smallest data size you operate on, you operate the flip-flops, then you go to SRAM, and if you have even huger, you go to DRAM. In this direction, you become from flip-flops to DRAM, you become slower and larger. So it's then more efficient to store large data in the DRAM because it's very small. It's less efficient to store this in the SRAM, but you are already quicker because you're on the chip. And it's even faster to have it in the flip-flops, very close to the logic, but it is relatively costly because you have for each individual thing, each individual bit, you need one flip-flop. So that was the difference between the SRAM and flip-flops. Now, if we compare flip-flops with latches, how do they compare? Where would you use a latch? So in which situation would you use a latch? Latches versus flip-flop? When to use what? When to use a latch? For different timings, it's maybe not the best way to formulate it. So I heard already asynchronous. That is what I would have said yes. So if you do not want to be in a clocked circuit, then you have latches. That allows for some, let's say, intermediate data storage independent of the clock. It allows for asynchronous circuits. It is usually faster than a latch, faster than a flip-flop, smaller than a flip-flop. So why not to use it everywhere? Difficult timing, yes. So why do we need, or why do we want to have the stuff clocked? I mean, if your operation, you have a logic block, your operation takes you, don't know, 1 nanosecond. For the next logic block, it takes 2 nanoseconds. For the next, maybe 5 nanoseconds. I operate the complete circuit. Also, this is sequential. I operate the complete circuit on, let's say, 100 megahertz clock, so 10 nanoseconds. The timing for every block is fulfilled, so that's fine. But why not, if the first 1 nanosecond is passed, the clock has operated, directly start the next one? That would be possible with latches. That is what we do in asynchronous logic design. Why not doing this? So latches tend to be unstable. That's one thing. We can solve this somehow. The main problem is if you have a really complex circuit and you need to predict the timing just because it can become unstable. Then in a latch case, you would need to consider from input to output all the logic in one step. So you have a huge logic tree, and you have to simulate all of this in one run. If you have a clocked circuit, and you always have parts that are processed and parts that are not processed, then you can break down the overall logic design into certain blocks, and your tooling becomes much more efficient. So you cannot even simulate such, well, if you think about what did I read recently, I think some NXP processor that is some billions of transistors. Huh? So even if this is logic, it means even still billions of gates. Huh? If you try to simulate something like this, it will take virtually forever, right? If you want to run this in one thing. If you cannot simulate it, you cannot be sure that after manufacturing this chip works, right? So you need urgently the simulation, you need the design tools that can automatically generate the stuff and so on. And this is only possible if you break it down into smaller parts. And to break it down into smaller parts, what helps us most is this synchronization stuff. So that is the big benefit of synchronous design, that we can predict the timing easily, have then fixed parts of the circuit with a predictable timing, and then we can plug this together. Huh? So maybe I give a quick, I try to draw a quick sketch to show what I mean. Huh? So, say we have some logic circuit, huh? And we have another part of the logic circuit, huh? And in between we need some storage capabilities because maybe we also have some feedbacks whatsoever, yeah? And we implement this as latches. Huh? So we have a bank of latches in between. We know for the first part here the delay input to output here. So let's call it I1, O1. So I1 to O1 takes us, let's say, something around, does not really matter, 1 to 5 nanoseconds. Yeah? Different passes inside, different possible delays inside, and so on and so forth. Yeah? And we have a second part here, and after this we have another part of latches. And for this we have I2, O2. We say I2 to O2 is maybe around, doesn't really matter, 2 to 3 nanoseconds. Yeah? So now we need to ensure for our latches that if the data which arrive here do not cause any metastability, right? So how to do this? We would need to consider the timing from I1 to O2. No? So the complete way we need to compute. We need to consider all the paths with all possible variations in the gates, with all the stuff inside. Huh? Okay? So this has kind of an exponential behavior, right? Because every gate that comes on top has a fan in, yeah? So that gets quickly huge. Now let's compare what happens if we want to do the same thing only with flip-flops. Huh? So if we put here the same thing, again, same timings, the only difference is that now we have a clocked circuit, right? So now the only thing we need to consider is we need to compute the timing I1 to O1, including the setup hold times, including the clock to Q, and the same for I2 to O2. Yeah? So we only need to consider these parts. And in this case, we know if this subcircuit works with a certain frequency, with certain input signals, with certain assumptions to the timing of the inputs provided to the circuit, And if we know that this circuit here works, so if the left part and the right part work, then we can just put them together. And we are done. We do not have to simulate from input to output. We only need to simulate from input to this one and from this one to that one. Not the complete way. And that makes it for the tools easier to partition the design, to handle the design. The quicker version would be with ledgers. Because here we said, okay, we have one goes up to 5 nanoseconds, the other one is 3 nanoseconds. But in this circuit here, the price we pay is the ledgers, the flip-flops are a little bit larger. And we can run the complete circuit only with the slowest block frequency. So with this 5 nanoseconds, meaning, yes, maybe 200 megahertz in that case. So the lower one to process from input to output is a little bit larger due to the flip-flops and takes at least 10 nanoseconds because 1 step, 2 steps. The upper one is a little bit smaller since we use latches and has only, but needs only 5 plus 3, so 8 nanoseconds at most. Right? So it's quicker and smaller, but we cannot implement it with our tools. So there's work on this, on such asynchronous circuit. There's special protocols, how to handle this, what to do, and so on. But overall, state today, and most likely still in 10, 20, 30 years, is that we have a clocked synchronous circuit because it has a lot of benefits for the design, for the verification of the design, for to ensure that the timing is correct. Okay, good. Yes. This is just a plus, should be. So we have effectively in the upper part we can consider this as pure logic, right? So in that case here we can consider it pure logic, because even a latch is pure logic. So we need to consider the overall timing. In the lower part, we consider the logic, plus we consider the timing of the clock tree. In sense, we consider also this clock to Q. So from clock signal arrives here to here something is sent. This is clock to Q, and setup hold time of the next register where we receive stuff. Okay, I also had a quick view on something like this here. I did not yet upload it. That was maybe a little bit quick and confusing, don't know. So this was this JK master-slave flip-flop, if you remember. What was the purpose of this? Or how does this on a high level work? So doing really the complete simulation is quite ugly, So I thought to provide something, but it would take me an hour just to do the simulation. So if you have time, probably at home you can just try to figure out which signal should go where. Best you start with some initialization, and then you try out what goes where. But from a high level, what is the purpose of the first flip-flop? What is the purpose of the second latch? What is the purpose of the second latch? And why is this overall then good? It's a little bit large, but a reasonable flip-flop. So let's start maybe. What is the purpose of the first latch here? Can you repeat, please? Yes. So it receives data from the inputs. At which point in time? Exactly. So in that case, we do this on a positive clock edge. We load the data into this latch. What happens here? When? Yes, so if the clock is low. Yeah? So it's level triggered, meaning this here acts if the clock is high, this here acts if the clock is low. Yeah? So what does this mean? If the clock is low, we load data into the master flip-flop. Yeah? Or in the master latch. What happens for this here when the clock goes low? Yeah, it stores the data. So when the clock goes low, this here is in a store state always. This here is set or reset, yeah, depending on the input data. When the clock goes high, yeah. So I just said it wrongly. Not if the clock goes high, if the clock goes low again. Yeah. So I start once again. If the clock is low, we said we load data here, we store data here, right? If the clock switches, so if the clock goes high, we store data here, and other way around, if the clock goes low, we store data here, we load, write data here. Yeah? If we write data to this slave latch flip-flop, we immediately provide them to the output, right? So after the clock edge, the falling clock edge, data are sent out through this and are buffered until the next time the clock goes low, goes high. Yeah? The first one in this period does not do anything first, and then takes the next chunk of data. So we've effectively, this is a latch, a flip-flop that operates on the falling clock edge, right? On the falling clock edge, we put something to the output, right? What if you, if we want to trigger this on the rising clock edge? So most of the time we have flip-flops that operate on the rising clock edge. What's the difference? An inverter, yeah. So we need to invert the clock, right? So instead of having the inverter here, we will put it here, same size. Huh? We have this here inverted, the second one non-inverted. Then on the high, on the low clock level, we would write here. On the high clock level, we would write here. On the low clock level, on the high clock level, we would store here. On the low clock level, we would store here. So in the rising edge, we take over the values from here to here and put it to the output. That's more or less the idea behind this circuit. Yeah. If you do a precise simulation, there's a little bit more behind, yeah, because you have this feedback with this Q and Q bar, yeah, which causes that you do not always directly have a set and reset, but sometimes you have, for some inputs, you still have a store, and so on and so forth. Yeah? But overall, yeah. So, for the, you mean for this, for having this on the rising clock edge?
Yes.
So for having this on the rising clock edge, effectively, what you do is, you take the same circuit. Yeah? Oops, it was too early, sorry. No. And then we need here a clock. So. Huh? So the only difference is that we move the NAND from here to here. Yeah. Yeah. So this would toggle on the rising edge. Yeah. Good. Okay. Good. And then we had a quick look. Yeah. And with such a flip-flop in place, what you can do is you can implement what we typically have. Yeah? We can implement some D flip-flop, yeah? Which is just, we always ensure that J and K are on a different level. Yeah? Then we have a D flip-flop. And we can implement a toggle flip-flop, because if you put at both input a 1, then at every rising, falling edge, depending how you design it, your flip-flop will change the internal state. This is useful, for instance, for counting number of clock edges or number of edges of a signal. If you want to know how many don't know ones have been transmitted for some reason, then you can do it with such a toggle flip-flop. So these are two very common flip-flop types that are used, data flip-flop and toggle flip-flop. I want to add once again, today, if you implement in particular data flip-flop, you will not base this on JK flip-flop. There are multiplexer-based structures that are much smaller, and so we can directly implement a D flip-flop too. But we skip this for this lecture. Okay, that was the recap of yesterday. Are there any questions left for the moment? No? Good. Then I can go ahead with the next slides. Is it? I've just forgotten to pass around this list yesterday. So you may just cross for yesterday too. Just give it around because otherwise I forget it. If I forget this and you remember, then just tell me, because I'm not used to have this, because in Germany we don't have these lists. Good. So, the next topic, what do we have so far? We have looked a little bit into design process. We have looked into memory types, into how flip-flops, latches, memory works, and so on. Now we can actually start to do something useful with this. And where we start is with synchronization and interfaces. So usually if you have a circuit, you need to put data into it and you need to put data out of it. I just have here some example. So for instance, if you look into your banking card, you will find a terminal similar to that one. Some connection similar to that one. This is effectively, you have for the smart card, you have some supply, you have some ground, you have some reset, that is just by standard given there. You have a point where you need to insert the clock. Then you have probably less pins. This one and this one might be removed because they are in the standard only marked as RFU, so reserved for future use. So most of the banking cards don't have this pin. Then you have somewhere a program voltage where you can program the card with, and you have one I/O pin. So you have a single wire to transmit data in and out, right? So you need to do this bit by bit. So for smart cards, banking cards, fully okay because we have not a huge amount of data. Frequently we have for, let's say, embedded systems, for classical systems, we have just a single pin for I/O. If you want to go for more complex systems, well, then you have multiple parallel I/Os, but the concept behind is more or less always the same. So we stay with only one pin. So what do I want to motivate with this? If we now want to send data into this device, then first of all, we need some protocols. So we need to define how do we send data in and out. For this, we have a few examples, not too much into deep depth, but at least that you know this, but towards the end of this lecture, or this lecture part. Then we have possibly something called clock domain crossing. So when we send data into the system, at least we have a delay. So the data on the system are delayed compared to the outside world. If we send them back, then we have probably some offset, timing offset. If this clock is not provided in a system from extern, but on the system itself, you have two different clocks. They are not in phase. They are probably have not the same speed. Still, you need to implement a communication between them. The same may happen on a chip. So if you think of your smartphones, there is on this CPU running on the smartphone, there is not one clock. There are probably 10, 15, something like this. So there are different clocks, and you need to communicate between different clock domains and ensure that data still are processed in the correct way. This requires some synchronization between different blocks, and that is where we will start with. And what we will also talk about is if you want to reset your system, then you can just do this asynchronously with some benefit drawbacks, or you need to do this in a synchronous way, or some mixture, and there we will also talk about. So that is what this slide effectively is about. Now, let's start with this clock domain crossing. What's the problem here? Well, we have asynchronous input for some reason with different clocks on chip, or we use at the same time rising and falling clock edges, and we are somehow in phase, or in somehow with the same frequency, but not in phase. The problem that may now easily occur in such cases is that you run into a metastability issue. Here, we need to be a little bit careful about this term metastability, because frequently we talk about metastability here if we are close to the metastable state for a longer time. That is, if I say metastability, that is actually an abbreviation for we are close to a metastable state for a longer time or are oscillating. Good. Now, what is the problem? Why do we run into metastability? Metastability is clear in the meantime, right? So what this in principle is. Or should I spend another word on that on a high level? Because we did this a little bit with the SRAM. You remember we had one point which we immediately leave if we go a little bit outside, and we have two stable points. There is one classical I call it classical drawing. I have this adapted from a French professor who is on random number generation. So maybe another view on this. So another view on this metastability issue is you have, just to have an intuition, you have some hill, and on the top of the hill you try to place a ball. And you know, if you are very, let's say, perfect, you might be able to put it somewhere on the top. But as soon as you have a slight disturbance, a slight wind coming from a side, then this ball will fall either in this or in this valley, right? So, in that sense, probably I make this here a little bit up. In that sense, this here and this here are stable states in the system. If our ball falls into one of the two valleys, it will stay there virtually forever. So you need to push hard to bring it out there. But if you have it in the top, if you put it into this metastable state, then already a small impact to this ball is sufficient to push it to the left or to right. Yes?
So the ball on the
Yes. Yes. So the ball in the top, this here, I can also draw this. This is metastable, and these two here are stable states. Right? Because if you put the ball there, it's stable. In between, this here is unstable. Right? because if you try to put the ball somewhere here, it will always go to the valley. So it's unstable. And now speaking back to our circuit, relating this to our circuit, if I talk now about a metastable state, what I mean is effectively we are somewhere around in the top half here, I would say. Yeah? So we are not necessarily really unstable. Yeah? We already have a problem if we are somewhere to the sides. Yeah? Because then probably some noise is already sufficient to flip our bit or whatsoever. Yeah? Okay, so back to circuits. So what is the problem we are now looking into? We have said we have flip-flops. We are synchronized. If we have flip-flops, we respect our setup hold times. We have no problem at all, right? That we already know. So we have some means to ensure that our circuit is not metastable. Now, if we have here such a case where we have two different clocks, what is the problem? The problem is at design time, we do not exactly know how these two clocks relate to each other. And if we do not know how the clocks relate to each other, we cannot compute the timing, so we cannot ensure that the timing of this flip-flop, the setup hold times of this flip-flop are not violated, right? This is our problem. In other words, it might be we have one clock, we have another clock. The one clock sends, the other one is probably the same frequency, probably another frequency, but it is offset in the phase. Huh? So if the clock here switches from 0 to 1, of course, this is also in reality not a rectangle. Nevertheless, the signal we send might be even slower. It has to load some probably long wire here. So it takes quite a while until it goes up to 1. In this period where this goes up to 1, our second clock changed the value. So we try to latch the value at that point into our flip-flop. It's neither 1 or 0. And it's even far away actually from 0 and 1. So we have two options. One option is that this goes a little bit up, takes long until it goes up, and then it stays in the uppercase. Or it goes a little bit up because we are somewhere on top, somewhere above ground. So we open some transistors, there will be some impact. So it goes a little bit up, but not sufficiently, and falls back into the ground state as soon as, and it falls back into the ground state afterwards. So it does not really latch the value into the input. These are the two main cases, yes? So this is the case we actually want to have, in that sense ideal, yeah?
But so opposite.
This is, exactly, so this is also a thing that this can happen. There's also one case I did not really draw because it's very unlikely, which is we go here into the middle and stay there. Yeah? This is very unlikely because, well, we have these, all these flip-flops are metastable, right? Have a metastable state in the middle, so this will resolve at some point in time. Yeah? It will not stay forever. That's also what we exploit later, by the way. And if it is somewhere in the middle, that is actually the most critical case, because if it stays in the middle, that means that we permanently consume power. We do not only know what the internal value is, we also permanently consume power. And even worse, we provide all the subsequent logic with some, let's say, VDD half. So what happens if we supply an inverter with VDD half at the input? Yeah. So something like this one here. I could draw the same with any other gate, but we just take an inverter as the simplest example. and we put this here as VDD half, yeah? Which is neither logical 1 nor logical 0, but somewhere in between. Yeah, the output is also undefined. Yeah? What does this mean? So this here is also approximately VDD half, right? What does it mean for a circuit or for our design overall? Yes, so the complete logic becomes metastable. Metastable means here, is this transistor open or closed? Not sure, yes. If you think about this trajectory, yeah, then effectively both of them should be resistive, right? So both of them should be conducting, yeah, up to a certain extent. Otherwise, well, the alternative would be that, well, or let's say other way around. How else would you achieve that here VDD half is arrived? Right? So you have here VDD, you have here ground. So you need some voltage divider, right? So you need somehow here two resistors, kind of. Yeah? So you open effectively a path from VDD to ground permanently for all the logic that is driven by your flip-flops, potentially at least. For all inverters, for sure. For NAND gates and so on, depends on the other logic, but you have potentially a complete part of your circuit drawing a lot of power, not only the flip-flop. So what we first ideally want to avoid, so what do we try to achieve in the following? What we ideally try to achieve is that we have, if here's a 1, and we have an input register, here's also 1. Yeah? So we want to have correct data. That's the final thing we want to achieve. Even higher priority has, we do not want that such a metastable state propagates into our circuit, into our logic. Okay? Because this is an effect, because we cannot have the timing precisely, we cannot completely avoid it. So there is no way to say we don't have this state at all. So there is a certain chance that it happens. If it happens, we need to have some possibility to avoid that we fall into a metastable state. We need some possibility to ensure that we are in the correct value. Okay? Is the problem clear that we try to solve? Yeah. Good. Now we have a little bit of statistics. Yeah? Part of this is, well, high level motivated, I would say. The first one is we have one flip-flop. Yeah? And I told you already that if we are in a metastable state, a small fluctuation will drive us into either the 0 state or the 1 state. Okay? So what we can say is, just take maybe this one here. What we can say is there is some probability which goes over time. We call this probability F. We just call it like this. We have an axis which is time, and, well, by measurements, by experiments, we can say that there is an exponential function over time, so that with increasing time, the probability that this metastable state is still there decreases exponentially. This is, well, a model. It describes reality quite good, but it's still a model. The steepness of this here, this is given by some tau. So, and if you write this as a formula, then you say the probability for a metastable state to be still there after a specific time is exponential function e to the power minus tr divided by tau, which is exactly this graph. Yeah? That's what we say first. Yeah? So we have a model for how long does a metastable state remain in the flip-flop if we do nothing. Yeah? So we put the flip-flop into the metastable state and wait, and after a certain time it should be gone. Yeah? And that's the description of that. Then we have a second thing that we call, where we ask effectively, how likely is it that we fall into the state? Huh? And so, if you think about some actual signal, some clock signal, for instance, and or data signal whatsoever, then some data signal is better. So I write here data. Yeah. We have some data signal looking like this, and now we come with our clock in the receiver domain, whatever frequency this had. For the moment, we neglect this. Yeah. And we ask, well, how likely is it that we get metastable? Then this is related to VR in a specific time window where we are in transition, right? Okay? So in this transitions here, certain range around the VDD half, we tend that to the flip-flops becoming metastable. Yeah? So we can just take all these edges and then we relate it to the overall length of the sequence. Yeah? So we say, what is the share effectively of time where our signal is metastable? Yeah? Okay, makes sense? And then we are effectively here. So a metastable state is triggered in this share of data, where T0 is actually the window here, the time window, and F gives the toggle frequency. So let's make a, let's say, more intuitive example. Yeah? We talk about seconds and minutes just to have something better in mind. Let us assume you have a signal that toggles all 10 seconds on average. Yeah? So we have 6 toggles in a minute. Yeah? The critical time is 1 second. Yeah? Then we have 1/10 effectively of the time is critical. The amount of time, so we have the frequency is 1 divided by, what did I say, 10 seconds. Time 1 second is 1/10 of the time, right? Where we have are critical. That's all. That is this formula, nothing else. Yeah? Okay, good. And now we bring the two things together, and we ask the question. Well, we know how likely it is that a critical signal, that a metastable state occurs for a certain time, and we know a formula for that such a critical state actually occurs. Huh? Probability. And now, well, what we can say is, or can ask is, how likely is it that this metastable state occurs? This formula. And stands for longer than that one, this formula. These are two events which are independent, because when this critical state occurs does not really matter for how long it takes to resolve it, right? So the things are independent. That means we can just multiply the probabilities. So what we come up is a multiplication of this probability and that probability is the probability that a critical state occurs and stays for longer than some time tr. Okay. Now we can go another step and can ask what is the mean time between two failures that occur? MTBF. That is something which is very typical for any systems where you have some reliability issues to compute some mean time between failures. And, well, if we now know the probability that a specific critical state occurs and stays longer than a specific time, we can ask for yet a rate how frequently such a event may occur per second. That depends on our receiver side clock, because the receiver side clock latches randomly specific points in time, and we have a model where every point in time gives with equal probability some metastable state that has this specific length. So what we need to do to compute this rate is we multiply the probability with the clock frequency. And the MTBF, mean time between failure, is just 1 divided by this rate. So we have this exponential function, the minus becomes plus, and divided by T0 Fd times Fc. That is how we come to such a description of the mean time between failure. Why do we do this? Because the goal of avoiding metastable states is equivalent to we want to bring up the mean time between failures or to bring down this rate. So if we achieve that the mean time between failures is infinite or that this rate is 0, then we are perfectly fine. We have no error anymore. That will not happen in reality. But we can bring the probability so low that it is unlikely to ever see during the whole lifetime of the system a single of these errors. And how this is done, I propose that we make a break just 5 minutes past half, and then we see how it's done. Yep.
All right for me to interpret time between.
Good. So let us continue. I've just a numerical example here. I catch this from somewhere from the web, from some technology. Well, with that, we have this formula for the mean time between failure. What would it mean for a standard technology, for a standard flip-flop? So, and there are some parameters. As I said, I just catch them for some technology. I don't even remember what precisely the technology node was, but it was not a really new one. So we have here this TR, 2.3 nanosecond. We have a tau with 0.31. These are things that come at the end from the technology. So how long it must take, or till what point in time we have to resolve the critical state, depends on how deep our path is behind our circuit and also on the technology. The tau effectively is a pure technology parameter. Fc is a specification, so what is our clock frequency I run with. Fd is the data transmission rate, so we don't have in hand. And the T0 is also dependent on technology, so which share of the edge actually brings me into a critical state. If I do it like this, then I come up with a mean time between failure of 20 days. So for one flip-flop. So every 20 days in your smartphone, one of the flip-flops would fail. There are millions or even billions of flip-flops in your smartphone. So you would permanently see some failure, yeah, if this would happen. Of course, not all of them are critical in terms of this metastability issue, because this is for data transmission, but some of them would be. Yeah. So this is still a bit of the problem we have, yes?
2 point, but then 0.3.
The tau is, it's already here on the slide. It's effectively the steepness of the exponential function at the beginning. So this is a technology parameter that defines the decay of the probability function at 0. Huh? Yeah? Okay. Good. This is not good enough for us, so we need to improve. Now what can we do? Well, at the end, we just put a second flip-flop. Why is the problem solved with this? So what we do is, we have still the sender flip-flop, we have still the receiver flip-flop. The receiver flip-flop has still the same problem. We put a second one here, yeah, and we say the problem is more or less solved. The reason is, well, the main goal was that our metastability does not propagate into our circuit, yeah, if we ever see such a problem. And the second flip-flop also, there is no logic in between. Yeah? So we have nothing which really can burn or so. Right? There's just the second flip-flop that is at the time where this one sends, maybe locked. Yeah? So, well, so what happens then is we send same as before, with a rising edge. We receive with a rising edge. I know it took a different period length for the receiver. And then, well, by chance, we latch on this rising edge of the signal. That causes some behavior, probably incorrect behavior, for our receiver signal, for Y dash. Then we have one clock cycle, effectively, to resolve this. And only after one clock cycle, the second flip-flop takes over the value of the sender. And here we are already stable. So the first flip-flop becomes stable. The second flip-flop takes the value from here, which is also stable now. And we are, from a metastability point of view, fine. From a data correctness point of view, other story. Huh? But from the point of metastability, that this metastable state cannot propagate into our system, that is nearly, I would say, solved. Yeah? Why nearly? Because we solve it on a probabilistic level. Yeah? And we can only solve this probabilistic event on a probabilistic level. Yeah? So, what happens in the mathematical sense? There are a lot of different models. I picked one from TSMC, yeah, that from TI, which I found most reasonable. Yeah. So, effectively, what does it say? We still have T0 FD FC. Yeah? So we still have T0 times FD is the probability that an event occurs. Huh? That does not depend on how many flip-flops you put here, right? Then we have an FC, that is the rate of this. Huh? So this does all not depend on the number of flip-flops we put here, right? Because we have here just one clock. So what depends on the number of flip-flops is this exponential function. We have a first flip-flop that, if it sees an event where we have metastability, needs a specific time to resolve. If it resolves, then we are anyhow fine. if it not resolves, we have a second flip-flop that again adds another time, yeah, and gives us more time to resolve this metastability now in the second flip-flop. Yeah? Make sense? Good. Then, what does this mean for the probability for some error to occur? So I would say I could even have put this TR to a larger value for the second flip-flop, yeah, because there is no logic behind. Yeah? So we have more time to resolve the issue because it anyhow doesn't propagate. Yeah? If we now still take this TR from here, put it into the same formula from the previous slide, then instead of 20 days before, with this synchronizer circuit, we are now at 91 years. Yeah? So way larger. So the probability that such an event is seen goes significantly down. If this is not good enough for us, yeah, what can we do? We just add another flip-flop. Yeah? Then every flip-flop gives us this exponential term on top. Yeah? And we have every time a significant gain. Yeah? Good. Why not putting an arbitrary large number there? Because it costs. Yeah? So if we receive data, just for visualization, I go back to the previous slide. If we receive data before adding the synchronizer, it took us 1 clock cycle to get them. Huh? With 2 flip-flops in place, it takes us 2 clock cycles, and we have twice the area for the input. With 3 flip-flops, we have 3 clock cycles to receive data, and we have 3 times the area, yeah, for this input. Yeah. So it means that every data you receive here is delayed by 1-2 clock cycles until you can start processing them. Yes.
Okay. So there is the more you put, the more waiting.
Yes. Yeah. Because this has to propagate through the flip-flop chain. Yep. Okay. Questions so far? Then let's go on. So the question is still, did we solve our problem? Partially. Yeah? So we solved the metastability issue. What we did not solve so far is, well, we have transmitted data, we have this metastability issue, we resolve it, but when are the data correct? We just don't know. Yeah? So, how to solve this issue? Well, at the end, we go to some protocol level. Huh? Good. Let me see. Probably I change the order a little bit. I start with, oh no, we make it as in order. Yeah? So, before we think about this protocol level, there's one thing I put before. Namely, if you now receive not one, if you don't receive only one input data, but multiple input data, if you don't receive only one input, but multiple inputs for our receiver side, so we send, for instance, x1, x2, we send a receive with our synchronizer y1, y2 dash for the first flip-flop, y1, y2 for the second flip-flop. Then what may happen is one of the signals is metastable, comes later, one of them is stable, comes earlier, and we receive, depending on this, a specific sequence. Due to its metastability and due to the offset in the timing of these two send signals, it might well be that what we receive ends up in unexpected data. So data which are probably even unvalid and put our system in a wrong state. So for instance, let's say we have these three states which are allowed to be received. So 0, 0, 1, 1, and 1, 0. They put our system into some state. We have no state 0, 1. This is just not supported. It is actually a don't care state, but, well, we did not properly handle this. Now, the sender sends only correct data. The receiver receives whatever he sees, and this is here 0. And then we have here, I just have switched this here, 0, 1, 1, 1, 0, 0, 0, 1. And that means we may have here, I think this should be just flipped whatsoever. That means we have a state that might not have been supported by our system at all. Now, what to do? We somehow need to ensure that if the sender sends data, we receive them correctly. If we have multiple signals, what we can add to do this, let's say, easily, is we can do something like this. We have on the sender side the sender flip-flops. We have on the receiver side receiver flip-flops, and we have now some enable signal on top. So we can say on our sender side, we apply data to these flip-flops, and we put the enable signal to high when the data are already here. So the asynchronous is sent with an enable signal. The receiver blocks here. So this is a feedback, and this feedback is controlled so that if we are here at 0, then we have the feedback, and only if here is a 1, then we latch in whatever comes here. So, sender sends data, the receiver enables with the first flip-flop. To avoid metastability, we have a second flip-flop. So we have 2 clock cycles. In the time of 2 clock cycles, hopefully the data are fully transmitted here that we may expect. So there is no metastability, the signal should be stable. And then here the enable signal switches the multiplexes, and we take in the data from here into the internal state and can start processing them. In that way, we are sure that we receive only valid data, and we are sure that no metastability can occur in our data flip-flops here, although we have only one synchronizer. Good. Partial solution. There's something with gray code. I just skipped this. It causes always only confusion. I will later tell a little bit about gray codes, and then we can maybe come back to that. But at that point, the last years, it always caused confusion, so I just skipped it. So this is one step. What do we not yet have? What is missing? So we know that if the enable signal is set here, the receiver receives the correct data. What we do not know is when are we allowed to send the next data, right? So who tells us now our receiver is ready to process the next chunk of data? We just don't know, right? And this is where protocols come into play. Because we somehow need to flag back from our receiver side to the sender side, hey, we are ready for the next data chunk. Yes, so we synchronize effectively here with, we have one synchronizer, and we can synchronize with this all the data. So you can have there more, because we block here until the signal is synchronized, and this gives us also time here to propagate the input signal, and we can rely on that this is stable. So what we are missing is some feedback, some form of a handshake to say how this actually, when we can actually send the new data. And I show you one version of this, which is very similar to also what is used in bus systems. So how does it work? We have two clocks. They can be the same frequency, they can be different frequencies, they can be in phase, they can be out of phase. This actually doesn't matter for the protocol. For here we have two with the same clock, same frequency, but a little bit an offset in the phase. Now we have a sender signal, X. We have some data available signal. We have a receiver data signal, and we have some data acknowledged signal. Between the different blocks, the sender is responsible for the blue signals, the receiver is responsible for the red signals. So, how does it now work that we can ensure that the correct data are transmitted and we are able to know when to send the next data chunk? This works as follows. The sender sends in the output flip-flop, in the sending flip-flop, the data to a fixed value, whatever it is. Then it has some final state machine, for instance, and puts the data available signal from 0 to 1. The receiver listens to the data available signal, possibly with some synchronizer if needed. When this data available signal is high, the sender knows there are valid data on X, so latches X into the internal register. Whatever it was before, it goes now to 1. So then the sender at a receiver puts the data acknowledged signal to 1. So says, hey, I have received the data, I'm done. Then the sender sees, hey, this here is at 1 with the next rising edge, possibly with some synchronizer on top. Says, okay, if this is 1, then I can reset my available signal. The receiver sees, oh, the available signal is down, I can reset my data acknowledged signal, and both know they are in a synchronous state. And then it can start the same process with the same data, or with other data. So in that way, we can data word by data word transmit the data, and can be sure whatever has been sent is also received. What changes if we go for a bus system? Can we be a little bit more silent, please? Can we be a little bit more silent, please? Otherwise, it gets really hard for me to speak all the time. Good. What changes if we have, instead of such a simple, let's say, one-wire system with X and Y, a bus system? So is it clear what a bus system means? So you have effectively a structure where you have one sender or one master on the bus, and you have a lot of clients on the bus, and then this master can talk to the clients, can read, write to the clients, and so on. And you have not only one word, but you have one bit, but you have multiple bits, roughly spoken. In such a system, you would have some address line to address which partner you want to talk with. And you have one data line where you transmit the data then to the corresponding address. And the rest of the protocol more or less can stay the same. So you apply address, you set the data the address available signal. The receiver says, okay, I'm here. Then you put the data, you put the data available signal. The receiver says, okay, I have received the data. And then you reset everything to the initial state. and you can run the next round of the protocol. So if you want to, this scales well, and if you look into current bus protocols, this looks very similar to a lightweight version of an AXI bus. There are extensions which then allow to send not only one data block, but multiple data blocks, but that already requires that your clock is somehow synchronized. Okay? Good. Questions so far? No. Then let's go on. Good. That was one solution. We have this classical handshake protocol. Something which is frequently, I would say, added on top. I have here written solution 2, but effectively they sometimes are also used together. We can use something like FIFOs. FIFOs, first in, first out buffers. The simplest form of this would be a shift register, but shift register does not guarantee that data are correct, that they are in the correct order, and so on. It is just a sequence of flip-flops, and it would not really help us here. There are specific class of flip-flops which are exclusively for read-write, not of interest for us. What is interesting for us is so-called concurrent read-write flip-flops, FIFOs. They can actually handle data in 2 clock domains. And there are 2 flavors of them, asynchronous and synchronous FIFOs. And since the synchronous at the end requires only such a handshake protocol on top, we start with the asynchronous ones, which do not fully solve our problem, but are the base actually for the second part. Okay. Then we have here how such a FIFO and the protocol of FIFO looks on a high level. So a FIFO at the end is kind of a buffer. So there is a certain memory, and if we send data quicker than they can be processed, then it might be that at some point our buffer is full. So we always have some full signal. This is here inverted. We could also say it's not inverted. I took here the example from some actual TI paper, so I take a not full signal. The same can happen if we process quicker than our sender sends data, that at some point our buffer is empty. So if there's nothing inside, we cannot further process. We need to know this, so there is an empty signal. Or in this case, a non-empty signal. Good. Then we are working in 2 clock domains. We have a sender clock called write clock. We have a receiver clock called read clock. We want to send data, so we need to send data out into our buffer. We have data out of our buffer, and we need some means to initialize the stuff, which is this clear signal. Now, if we look into the timing diagram here, then what happens at the beginning, there is some reset of the FIFO, which is just we enable the not clear signal. And then this is put to 1, and all the rest of the time is not clear. The write clock, write is not a classical clock with a fixed period for its asynchronous flip-flops, but it toggles if data should be written. And in that case, data are written with the falling clock edge. So we have here a buffer, and if we write into our buffer with the falling clock edge, then we have data 1, data 2, data 3, and here data 4, data 5, which are written into our buffer. Now our buffer in that case has only, I think 4 it was. Let me quickly look. Yes, 4 can only process 4 data words. Or probably 5, whatsoever. So, no, I think it's 4 data words. as soon as the first data is written into a buffer, the buffer is no longer empty, our not empty signal goes up. Yeah? So we flag to the processing unit on the receiver side, we are ready, here are data, you can start processing. Yeah? The processing unit on the receiver side decides at some point of time, hey, I now want to read the data. Yeah? So it pulls down the read clock and reads out the first data chunk. Yeah? If this data chunk here is read, it's not overwritten, but it's invalidated, I would say. Yeah? Or removed from our stack, we can think of. So the data are read from the stack, since we have written 1, 2, 3 data chunks. There are still 2 data words left in our buffer. Now the processing unit is probably a little bit slow, and we write more data in the meantime. We write data value 4 and 5. We have 4 words in our buffer. Our buffer size is only 4. So we need to block our sender from sending further data. This is why at that point the full signal goes down. So it tells the sender, hey, stop. You need to wait for the receiver unit to process further. And then at some point our receiver starts working fully on the data and reads out in every clock cycle whatsoever one of the data words. So reads D2, 3, 4, 5. As soon as this is the next data word is read, the full goes up again. So the sender can send again data because we have now room for more. And in that case stays high because no other data is sent. Since no other data is sent, at some point all the data from the stack from our buffer are read. So our buffer becomes empty again, and we are back with the empty signal. Now we have to wait for more data, or we can do other stuff or whatsoever. But this is how this on a high level the input-output behavior of such a FIFO looks like. Okay. Yeah.
Why do they read D1 first and then the break?
So what the motivation is why here this D1 is so long, actually? Well, here I think it is only to show the effects. In practice, this can happen, for instance, well, your receiver clock is slower, or you have a protocol where the first byte or the first word you send is responsible for configuration on the receiver side, and the rest is data that are processed 1 per clock cycle. That could also be, so that could be a practical reason why this is long, but here I think it's only for showing the effects. Good. Then we should have a quick look how to implement this. The first part I will do pretty quick because it's not the state of the art. It's a little bit old, but I think that's very nice because it's actually, yes, an asynchronous design, a little bit related also to this. No, it's an analog design which is related to the sledging stuff. Good. What do we see here? We have in the upper part we have our data buffer. In the lower part, this is actually control logic. We talk about the control logic later and start with the data path. So, in the way this is built, we have, well, you see here's an RS latch. Here is an AND gate blocking actually the input, right? We have here, let's go here, we have here an inverter. This inverter causes that these two signals here are different, so that we have always the R and S or R and S bar on a different status. Huh? So we have not a store input or we have a 0, 1 input, but it's always on different values here. It's just a data latch. So now our data latch is enabled from our control logic. If it is enabled, the data from the input are latched here. If the next enable comes, the data from here are put here. If the next this here is enabled, the data from here are put there, and so on. And finally, we are at the output, and at the output we have the value that we had written somewhere in the past here at the output, and due to this inverter here, it's also correct. So that if we start a 1, we receive at the end a 1, and vice versa. This is the data storage structure, and we can have multiple of them. It's not necessarily only one. Good. That is the data path. Is this okay so far? So what happens in this control path? So, yeah, first, probably I should show this here. If the value here is a 0, these two values here are 1, right? Both inputs of an RS NAND or RS NAND latch, NAND-based RS latch, both values at 1 means we are in the store state, right? So, if this is 0, we are in a store state. We take the data from the input to that only if this value here is 1. If this value is 1, means C1, C2, C3, C4, if they are 0, we enable writing data from one stage to the next stage. So, then we can just focus on this part and can put the state, can remove the inverters and the upper part. So, we start with a clear. If we put the write clock to 0, we put the clear to 0, we put the read clock to 1. What happens? Well, it causes that at the end, I think I have it on the next slide written, that effectively all is reset. So where did this come from? Yeah. So let me see. If we have here a 0, then the output will be a 1. If we have here 0, the output will be a 1. If we have here 0, the output will be a 1. If we have here 0, the output will also be a 1. Right? So all the outputs are set to 1, which is this step. Right? Then we have, I need to think one quick second what I wanted to say here. Whatsoever. So, just need to quickly think myself what I actually wanted to say here. So if you have this at 1 before, then we drive all the other wires into the 1 stage. It just should have added an intermediate step to make this visible, but this I think comes through this clear being 0 then at some point. So you have this, this is the next step, and then you have effectively initialized your FIFO. So what you have now is, of course this is still 0, but you have the full signal at 1, not full signal at 1, you have the not empty signal at 0, and you have the read clock and write clock comes anyhow from external. Then we can change the clear to 1, so it is not clear. If we move the not clear signal to 1, well, we can effectively remove it from the NAND gates, right? Here, 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 and here. because if it's 1, it has no impact on the output anymore. Right? So a signal in a NAND gate that is 1 does not influence if the output is 1 or 0. Yeah, that only depends then on the other signals. Right? Is this okay? Yeah? Okay. So we can remove it there. That simplifies a little bit the drawing. Okay. Then we set the write clock to 1. If we set the write clock to 1, then we take from the clear input, we take now the value 1 into the value q, right? Now all the values of the next NAND, and in particular this C1, becomes a 0, right? If C1 becomes a 0, then we clear the flip-flop. The flip-flop becomes a 0, yeah, the clear. For this, yeah. Since now the C1 becomes 0, the output of C1 is a 1. So the output of, I just point here, the output here becomes a 1. Then here we have a 0, and we feed this back, and this here gets 1 again. So what we have here is actually what it causes. The important point is we have a sequence 1, 0, 1. What does it mean for our data path? Block, open, block. Right? So for a short period of time, not depending on the clock, just depending on the timing of this path here, we propagate in our data path the input to the output. And then we block again. Then we have the same here. We have 1 switches to 0. And this 0 now propagates here, puts here 1. The 1 causes that here we become a 0, and we flip it back to a 0 again. Yeah? So, and that propagates now through. So we have here written to the first stage and block, written to the second stage and block now. Then we have here for the third state the same, and for the third state also. So effectively we propagated our signal through, and when the signal is here at the last stage, we put here the not empty signal to flag that there is now data available. So we have propagated data from input to output and flag data available. Then, well, our clock signal may go to 0 again. This last here, this flip-flop, by these two inputs, becomes a 0. So we lock effectively this NAND gate. Good. Then we write another time data. We have a second time we go from 0 to 1. If we go from 0 to 1, we have effectively the same process as before. Data fall through this FIFO, but since this NAND here is locked by the feedback, the data is only propagated until this. So if you think about the data path, the first data was propagated to the last stage. The second data is propagated till here, right? Because we have the sequence 1, 0, 1 only for this one. For this one, it does not become 0 because we have forced the output to 1 by this feedback. So that is what happens if we write the second data. Now let's read. So we put our read clock to 0. If we put our read clock to 0, we disable this signal. So we put this here to this signal here to a 1 again. So the feedback is effectively unlocked. if this feedback becomes unlocked, where am I? Oops, here. Then as soon as the read clock goes up again, so not as long as the read clock is 0, but when the read clock goes up again to 1, this flip-flop here sees now 3 ones at the input, right? If it sees only ones at the input, the output should go to 0, right? So we move effectively the data from this stage into the next stage in the data path. Yeah? So we have again here this transition to 0. This transition to 0 or effectively causes that in the next stage, in the previous stage, we have also unlocked this signal, and the data are propagated effectively from this stage into that stage, and then this last stage locks again. Yeah? The stage before becomes unlocked, so new data can propagate till here. Yeah? So, from a, let's say, unlock perspective, is this pretty nice thing, because you only have one clock cycle and then the rest is just completely controlled by a pure analog circuit and the thing works. Yeah? From a cost perspective, what might be a drawback? Yeah, there are a lot of gates. Yeah? So we have effectively also here one latch for each stage. What happens if we want to extend our depth of our data path by, don't know, by a factor of 5? I did not fully get it. I did not hear you, sorry. Can you repeat? I did still not get the first word. Restricted. Now I got it, sorry. sorry. So, no, I would say we can have an arbitrary length of that. Of course, you have some analog behavior in there. Maybe then it's not arbitrary. But let us assume we want to have here, well, if we want to have 5 stages, then we need 5 times this, this logic circuit here, right? If we want to have 32 stages, we need 32 times this logic stage here. Yeah? So it scales linearly, that the control logic scales linear with the depth of our data path. Yeah? And the data path requires latches and some additional NAND gates. So the overall thing is relatively large, right? And does not scale well. Yeah? So if you want today, don't know, this here is, let's say, you have 32-bit wide register, yeah, because that's, or 32-bit wide data path. Then you would write to this 32-bit data at a time. Yeah, so maybe I go back a little bit. So just go up here. So usually if you want to have a, let's say, 32-bit system, yeah, then your FIFO should also be 32-bit to cover all the one data word at a time, right? So one data word would mean that we need 32 of these constructions to cover the full word width. There's hardly a way out. So that's just the memory we need. On the data path side, and on the control path side, well, per data word we still need only one of these stages. But now you want to not only store one word, but you want to store, don't know, 1K word. Then you would here need 1K times number the rows, and also 1K times here number the rows, number the columns. Sorry. So it scales as well data paths as the control path scales linearly with the number of data we want to have. And for large sizes, that is just, yeah, we can do better, let's say like this. And this is why this is actually not state of the art, but a little bit old-fashioned. What is state of the art is called FIFO with a static memory. Yeah? So this is a visualization. Before I go into this visualization, I think I should, from my experience from the last years, make clear what this visualization actually means. So for this FIFO with static memory, we have a static memory and SRAM. Yeah? And SRAM in reality means we have SRAM cells somehow connected with word lines and bit lines, and just as we did this before, we had this before at some slide, right? So usually the control comes somewhere from the middle. That's why I have here this word line in the middle. Doesn't really matter. So this we can imagine as we have a memory structure. I just write here SRAM, that you remember probably what it was. So this you can visualize as a structure where you have, usually we count from bottom to up, so I make it like this. So you can visualize this as we have an SRAM counting from address 0 to address n, right? That's just how we usually, if we say we read a specific data word, is word n. Okay, good. And this you can now translate into, we just wrap it around. So we put this address here to 0. So this one here goes 0. Then we have the next, this here would be address 1, and so on. And the last address here is address n. So this one goes here. Is it okay that I can visualize my physically looking memory like this as such a cyclic structure? It's just a visualization. Of course, in a physical world, it would stay like this here. Like this. But I can visualize it in that form to make it better, readable. And then I can put here a pointer. And this pointer is just an address pointer. So it tells me what is my current address. Okay? So this is what we have effectively also on the slide. So we have an SRAM and we have a pointer on the SRAM. Actually, we have two pointers. One for address where we want to write to, one for address where we want to read from. Okay? So whatever is written to the SRAM is written to the address of the write pointer. Whatever is read from the SRAM is read from the address of the read pointer. No magic. It's just we have an SRAM and we read-write from specific addresses. Just a different kind of visualization that they might be used to. Okay, now to implement this here, what do we need? We need some SRAM and we need something ideally called dual port RAM. Dual port RAM means just this piece of SRAM is designed in a way so that I can read and write from different addresses at the same time. So I have dual ports, one input port, one output port, and each of them can be configured with a specific address. Yeah? To this dual port RAM, I provide for the input side a counter value that implements the write pointer. I implement input for the read side, a counter that implements the read pointer. Yeah? So far? Okay, right? Then, well, what do we need to do? If we want to write, we need to just put data to the data input. If we enable the write clock, our write counter is incremented. So data are written into the SRAM, and we increment. Write operation done. If we want to read, we apply a signal to the read clock. At the same time, we read the data, so data are read. Read point is incremented. We are at that point. Huh? So we can read and write freely from this memory. Huh? Now we need to ensure two things. We need to ensure that we read valid data, and we need to ensure that we do not overwrite data. Huh? If we want to ensure that we do not read invalid data, we must actually guarantee that our write pointer is always at least one ahead of our read pointer in this cycle, right? Then we have always valid data. So, in other words, if the write pointer is not at least one ahead of our read pointer, we should flag here this thing is empty. On the other side, we need to ensure that our read and write, that our write pointer does not overwrite data. So, in other words, if our write pointer is at the position of the read pointer, we are not allowed to write anymore. Huh? So, if the write pointer becomes the read pointer, we should flag here full. Huh? That's this flagging logic. And in that way, we now have, well, with this part of logic and an SRAM block, we have implemented a FIFO that fulfills the specifications from before. Why is this better? Well, for large memories, an SRAM scales much better than the ledgers from before. Yeah? So the data path is already smaller. On top, here, we only need to store a read or write pointer instead of having this linearly scaling logic, control logic. A read or write pointer scales logarithmically with the length of the RAM, meaning if we double the RAM size, we have to add 1 bit for our counter. So in that sense, this here is better for large memories. For small memories, maybe not, but for large memories, this is definitely preferred. Good. Still, we have an issue. This is still asynchronous, meaning, that is what I already explained, meaning we have several problems here. As long as the clocks are the same, read and write clock are synchronized, all fine. The problem comes if the read and write clock are not synchronized. Because then, the first thing is, with our write clock enabled, we change the empty signal. The not empty signal is evaluated in the read clock domain. So that might be asynchronous in the read clock domain. If we read from the RAM, then the full signal might be or is controlled by the read clock domain, but evaluated in the write clock domain. So this is also asynchronous. What can we do? Well, we put a synchronizer there. We put a synchronizer in the empty and full signal, and that's more or less fine. One other point I may talk a little bit about this later, because here it's a little bit maybe confusing again. With these counters, if you compare them and they come from different clock domains, this comparison might cause wrong results. Because one counter is in transition, the other one is already stable, and if you compare them, the result might, for a short period of time, flag the wrong outcome, causing a wrong value for the flex logic. Whatsoever, alone that we have now this synchronizer, what does it mean? Well, we need some clock for synchronization, right? If we need a clock for synchronization, we cannot go ahead with what we did. What we did before was we triggered with a rising clock edge of a falling clock edge, we triggered a read, and with a rising clock edge, falling clock edge of the write clock, we triggered a write. But how to synchronize on the read clock if this is not permanently there? That's just a possible. So what you need to do is, if you want to synchronize this, you need to add on top a permanent write clock, a permanent clock from the read domain. So we have now a permanent clock from the write domain, a permanent clock from the read domain. And to trigger the actual write and read action, we have a write enable and a read enable. And then we are in a synchronous FIFO, and we can have everything fully synchronized, so that we do not run in such metastability issues. Good. So with this, we have solved this problem of synchronization, and I think you need to hurry for the next lecture, right? So we have tomorrow then reset synchronization, and may talk a little bit also about some protocol stuff. So see you tomorrow.